Let's start with what you already know, and that is that current, by definition, is dq/dt, or if we're dealing with a static current. And for today, let's just deal with a static current. This would just be charge over time. Now, I'd also like to, at the same moment, define something called the current density, capital J, which is defined as the current per unit area. Let's put it on my desk, please. We're going to have to learn what time school starts around here. Now, to really understand the stuff that's in the textbook, or the questions that I asked you about current density and drift velocity and all that, we're going to need to have kind of a firm understanding of what these two ideas are. This is a measure of how much charge generally passes a single point in the circuit in a unit of time. And this is not the same measurement. The current density takes a look at the flow of charged particles through a cross-sectional area. There are times where one is better to use than the other, but not that often. We're not really going to look at current density very much this year. The actual definition of current density is not as easy to fully appreciate, and this will never come up as far as I know. I've never seen it on the exam, but this is the actual definition of current density. It's taken as an integral based on the assumption that the current isn't the same everywhere within a wire, that the current density changes on different parts of a wire. This is an old idea of what was happening in the wire. Nowadays, the modern idea of current doesn't really utilize this because we know that current isn't a flow of charged particles through the wire. Current is actually on the outside edge of the wire. All right, so I don't think we're going to see this very much on the exam because it doesn't really represent what's actually happening. But we're going to use this because the theoretical interpretation of what's happening based on historical reference is really what the chapter was about and what the unit was about. So I want to start by this recognition that if we have a piece of some conductive material, and for the time being, let's assume it has a uniform shape with a cross-sectional area A and a length L, and that it is filled with charge carriers. Now, we know from having a conversation about this already that a charge carrier doesn't actually travel in some kind of straight line through the wire. That if there's an electric field in this direction set up inside the wire, the charge carriers generally drift this way. They're electrons, we know that. But they don't go in a straight line. They're actually bouncing around, striking something, often going backwards, forwards, in some erratic path. But that they generally drift in one direction. Interesting little tidbit. The acceleration on the particle is actually really, really high. When you consider that the acceleration is going to be the force divided by the mass. And so you're going to get a lot of acceleration. These particles can reach a speed of like 10 to the 6 meters per second between collisions. But the number of collisions is so high that in a standard household wire, the drift velocity is somewhere around 10 to the negative fifth or 10 to the negative fourth meters per second. So although they travel really fast between the collisions, they are doing mostly collisions. And they're definitely traveling backwards as often as they're traveling forwards. So this disconnect between the drift velocity and the actual velocity is so big that, again, it's kind of hard to fully appreciate what's really happening in the wire. And I'm not sure that any of this is really happening in the wire because we know that the electrons are actually traveling along the surface of the wire. So I'm not sure if the collision and the idea of drift velocity is particularly valid. However, we're dealing with this theoretical idea of what this is. So I'm going to define this term, and I'm going to use the symbol that's in the book, which is kind of some weird fancy script N. as the number of I'll say electrons, but let's say they're going to use the word charge carriers per volume. Now, this is something that is particular to a material. So some materials are going to be more rich in charge carriers than others. And therefore, this is very fixed on the material. Now, if I want to know how many charge carriers are available in a piece of wire, we have this piece of wire sitting right here, then I could say take that value n and multiply by the volume of the wire. And this would give me the number of available charge carriers. If I multiply this by the charge per charge carrier, I would get generally the charge available in a piece of wire. Now, I'm just taking kind of some definitions of ideas, big ideas here, just kind of multiplying them all together. I define the charge density as the number of available charged particles per volume, like an Avogadro kind of thing. I'm multiplying that by the volume, which I'm going to establish here has to do with this cross-sectional area and the length of the piece of wire. And then I'm multiplying by the charge per electron. This gives me the total available charge in a piece of wire. So, I really want to write this as NALE. In fact, maybe write it as NE and then multiply that by the physical constraints of the wire, AL. Now, this would represent the charge density. Not the number of particles, but coulombs per cubic meter. We know that we're dealing with electrons, which is why we can write it with E, but it really is the charge density. When I talked about this the last time, I just used charge density the whole time. But here I'm being a little bit more focused on what was probably in your textbook. Now, for all intents and purposes, this represents, and every time I put a square around something, it's probably one of those things that you should tuck away. It's not on any equation sheet. It's kind of stuff that will help with the homework kind of questions. This is the total available charge in a piece of wire. Now, if I assume that an electron, say, starts here, actually, electrons are going the other direction. If I say electron starts here and travels across this piece of wire, I think all of you will agree that we could define the drift velocity in terms of how long it would take for that electron to make the trip. You guys okay with that? Also, we already have a definition for current based on how long it would take all of that charge to pass one point in the wire. So if Q represents all of the available charge in the wire, and we know that they all have the same average drift velocity, then I could say that current, which is Q over T, would be the charge density times the size and shape of the wire divided by that same unit of time, T. Now, this would give me an expression for current in terms of the charge density, the cross-sectional area of the wire, and now the drift velocity. Any question about what this suggests? Now, this is a good place to say, let's call that equation 1. Because it really is a fundamental idea of current in terms of the microscopic. It also has this piece That's about the fundamental nature of the material in which the current is passing. And also, as you can probably imagine, I could write this in terms of the charge density by just dividing both sides by A and getting the charge density times the drift velocity. Either way, writing this in terms of the current or the charge density, they're really about the same thing. Any questions about any of that? Now, charge density, like I said, is an older idea, but it's really rooted in the expression for where current comes from. So I want to start kind of with this idea for a minute that we can write current or current density in charge of these fundamental ideas of what's happening inside the wire. But the truth is, the drift velocity is also a function of what's going on in the wire, as much as the charge density is a function of the material itself. We don't really know either one of those. I mean, we can measure cross-sectional area, and we can measure current completely divorced of knowing what's actually happening microscopically. So if we set up a circuit and I give you a chunk of Play-Doh like we did last year, you could figure out what the drift velocity of the electrons is experimentally, but there'd be no way to actually get down there and measure it microscopically to see if it was true. I mean, there's just no easy way to do it. Now, there are separate experiments that will allow us to measure N, and separate experiments that will allow us to measure the elementary charge. So those could be measured, but still, there is just no way to actually measure drift velocity. It's mostly a theoretical construct. However, just giving you all the pieces. So with this piece, I'm going to take a break from this for a moment and talk about what's actually happening to an electron in the wire. An electron in a wire accelerates. Let's say the electric field is this direction. So the electron is going to experience an acceleration in this direction. And during that acceleration, it's going to experience an increase in velocity. The drift velocity represents the average of that velocity, not the max, but the average. So we could consider the drift velocity to be the average acceleration times this idea of t, which actually your book writes as the Greek letter tau. Basically, what your book is trying to say is that, look, the charge is going to accelerate until it hits something big. It might not be very long, but it'll accelerate right up until it gets there. And during that time, its velocity will change, but over the span of this short amount of time, which we'll call the tau, the time between collisions, the particle is going to experience an average velocity, and we'll call that the drift velocity. Now, this is not really what's happening. We know the particle is sometimes going backwards and sometimes going forwards. This is taking an average over all accelerations over the course of all the charges in a wire, that the drift velocity somehow represents this acceleration. And moreover, we know this acceleration from Newton's second law can be written as the force on the charged particle divided by the mass of the particle, this being the mass of the electron specifically. And in addition to this, we know that the force is the actual elementary charge times the electric field in the wire. Meaning we could write drift velocity in terms of fundamental concepts. That's a new noise. All right, so this is a different way of expressing the drift velocity. Now, this way is totally meaningless. Let's be completely honest here. This is completely based on knowing something else we can't measure, which is how long it takes between collisions. Again, as a construct goes, this is difficult really to consider. But this is also taking the idea of what's happening in a material and turning it on its side. Instead of talking about the number of available charges and how fast they're traveling, we're talking about how difficult it might be to pass an electron through a piece of material. This is trying to build an idea of what resistance might be. Then in a wire, the reason why we don't get a higher drift velocity is because of all these collisions. The more collisions there are, the more difficult it is to pass an electron through the wire. So when we consider T, the smaller T is, we know the smaller the velocity is going to be as well, but it suggests that the material is not letting electrons pass as easily. Perhaps it's more dense or has more material in it that the electrons have difficulty getting around. So resistance could really be considered how often those electrons are colliding. If they're colliding more often, then T is a smaller number. If they're colliding less often, then T is a bigger number. All of that relates directly to the drift velocity. And trust me, you might wonder, why are we even bothering with this? Well, there's a reason. Look, we've got this fundamental concept here, E over M. I don't know if you guys remember from chemistry what E over M is. I always ask about things about chemistry, but do you guys remember? Where's my chemist? Does that jog your memory at all? AP chemist? Anybody ever heard of the Millikan oil drop experiment? I don't know if it comes up in chemistry any longer. I have no idea if it's part of the curriculum or not. All right. You guys probably recognize that all of this is based on this idea of charge and the electron, but the electron was a theoretical construct. Millikan set out to try and determine what the charge was on the individual electrons. This is before the plum pudding model. This is before the Rutherford's theory of an electron. This idea that there was electrons and protons that were microscopic particles was beginning to be theorized in the late 1800s, early 1900s. Millikan devised a method to try and figure out the actual charge on the electron. The first experiment to do so. We right now have built a relationship for the drift velocity in terms of this ratio. So Millikan knew about this research and was attempting to find this ratio using something that was not a circuit to see if they could calculate the drift velocity. I don't think that's exactly why he was working on it, but that's, the extent of it. So tuck this away for a minute. Drift velocity is there. And here's what I want to do. I want you to consider that, how do I want to say this? We had an expression for the drift velocity just a minute ago. That was NE times the drift velocity. Sorry, the current density in terms of the drift velocity. So we could write this in terms of drift velocity and do substitution. Now I know, you're wondering why are we bothering to do this? Just give me one more second. If you solve this for the current density, you get NE E over M times tau, all times the electric field. Now, at this point, first, it has two measurements based on the material. Average time between collisions and the charge carrier density. It has two values that are fixed constants. All of this is known as the conductivity of a material, which, by the way, is the inverse of the resistivity of a material. Now, we know resistance is easy to measure. resistivity is related to resistance. So if we consider this current density for a minute, we could write this as, and by the way, the symbol for resistivity is lowercase rho. So we could write this as J equals 1 over resistivity times the electric field. However, and he did so by atomizing small droplets of oil, basically using just a spray bottle and creating a fine mist of oil droplets. He knew that the oil droplets, and when we're talking about oil, any oil would have worked, but I can't remember the type of oil we tend. When we do this lab, when I did this lab in chemistry, I want to say we just used like a cooking oil or vegetable oil worked. But once it goes through the atomizer, it gains a small amount of charge. And you have to set up a location with an electric field. So you do this usually between a couple of large plates, and you put a potential difference between them. It doesn't have to be much. A couple volts is enough. These little particles are tiny, and you're trying to get them to a point where they are balanced. So you adjust the electric potential until a group of the little particles hover. The bigger particles will continue to fall because they're too heavy. Remember, we're looking at mg versus QE. But each little droplet is a different size. So ones that are smaller than the one you've kind of tuned in, they drift upwards. And ones that are bigger, they drift downwards. And you measure the size of the droplet using usually a microscope. And you etch on the glass a couple of measurements for how big each one of these little droplets is. And by looking at the density of your oil and the size of your droplet, you can usually figure out M to pretty high precision. And by tuning the electric potential and knowing what G is, you can figure out Q. Now, this doesn't give you the charge on the electron. It gives you the charge on the droplet, and you have no way of knowing how many electrons were scraped off in atomizing that droplet. So Millikan spent probably way more time than you guys would have looking at individual droplets, figuring out how some of the droplets were experiencing more force than others, and began to discriminate between the number of charged particles on each droplet. Over the course of weeks, he was able to develop the ratio of E to M, which ends up being the de facto value that we use today. That you can't get a better ratio from this experiment or other experiments. You can measure M and E in separate experiments, but this ratio is really pinnacle towards figuring out, A, that the electron was really, really, really small, but had a lot of charge for its size. So the mass is times 10 to the negative 31, but the charge is times 10 to the negative 16. So for its size, the electron ends up being very charge-packed for a particle. And, oops. If I solve this for the electric field, I'll go back to my my picture from earlier. I have A here. That's cross-sectional area. L here. That was the length of my sample. I could write this as E times L equals rho times L times current density. Let's multiply both sides by the length. If I do that, this becomes the electric potential applied to the piece of wire. Now, if I multiply and divide by A, you guys see what I've done there? Then I could write this as rho L over A times I. This It's how you make a resistor. We talked about this last year a little bit. This is the theoretical explanation for what a resistor is. A resistor is a chunk of material that has a certain resistivity. L represents the length of that material. A is the cross-sectional area of that material. We'll define that as a resistor. The resistivity has a direct measurement in terms of conductance. L and A are physical constructs for its size. This is a theoretical derivation of Ohm's law based on what's happening at the microscopic level, and has in it all the pieces that we saw about resistivity. Now, we tend to think of this in reverse, meaning we don't actually measure this. We measure resistance and then solve for resistivity. And that's how materials get their resistivity or their conductivity. But ultimately, this is all the pieces you should need to deal with the drift velocity questions. Now, I'm not saying that they're going to be easy, but they're going to be some mixture of these pieces. Yeah?
From the second line onto the third, did you multiply by A or divide by A?
From the second line to the third?
Yes.
I did both. What I really did was this. On the right side, hold on. It's rho times L times J, and I multiplied by A over A.
Oh, okay, got it.
Is that okay?
Yes.
Just so I could work in current instead. Now, from last year, and if not last year, then this year for sure, we need to know this. We know that resistance is related to the length and the cross-sectional area of your material. And that's not a surprise. More cross-sectional area means that there's more pathways for electrons, and therefore we see the resistance goes down. Increase the length, and we know it's harder for electrons to get through, so we're going to increase resistance. In fact, you should be able to figure out why series and parallel work out the way they do. Parallel essentially is increasing the cross-sectional area. That's why resistors in parallel have less resistance total. And resistors in series is more or less just increasing the length of your total resistor. Same thing we did for capacitors. So why capacitors increase and decrease with parallel and series, we can apply it based on their structure and shape. It shouldn't be a stretch that we now have a definition of resistance that is based on the physical construction of a resistor, and we had a similar definition for capacitor based on the physical construction of a capacitor. And both of them predict what we would expect for capacitors and resistors in series and parallel. All right, Luke.
Yes.
That's going back through it. I went in the opposite direction of what I did the first time. That might not make the questions easy, but is there a question on the homework you'd like me to talk about? I'd be happy to.